Okay, once again, we're going to talk about energy. So this is Unit 3, Work Energy and Power. This is the fourth video in that unit that we're doing. This is going to be part number 3, Energy 2. So I gave you kind of an introduction to what energy is in the previous video, video number 3. And this one we're going to kind of get a little bit more in depth about this stuff called mechanical energy, which is those 3 red ones that we talked about at the very end of the last video. So some learning targets for you. Same thing as last video. I know what energy is. I can calculate energy, and I know the total mechanical energy. In the previous video, I brought up 3 types of energies that I wrote in red. I said they were the kinetic energy. That was one of them. And the other 2 were what I said was gravity potential energy. And spring or elastic potential energy. Those mean the same thing, but I like to call it spring potential because we usually talk about springs. And when we talk about spring potential energy, we have to have something that obeys Hooke's law to really do any sort of analysis on it at our level. So that means that pretty much it's spring potential energy. So things that do elastic deformation do not usually obey Hooke's law. So something like your car, while the outside, the body can be pushed in, it can be dented, it can pop back out. It'll store energy while it's being pushed in, has that dent in it. When the dent's popped out, it does work to relieve that energy, but it's not going to be Hooke's law. It will not follow Hooke's law. It's not linear. The force is not going to be directly proportional or linearly proportional to the displacement. So in a sense, the only things that usually do that and can be approximated that way are springs. And so we'll just call it spring potential energy. Anyways, as you see, I've got 2 different columns where I put red kinetic energy and then blue the 2 energies that have the word potential in them. And the reason why I did that is because I wanted to split these 2 up and talk about these energies differently. First thing that we're going to do is say that we have 2 broad categories that we can place things into. That we can place energies into 2 big, overwhelming, large boxes that we can put them into. On the first box, it says kinetic. On the second one, it says potential, and all of our energies will fit in one of those 2 boxes. In the previous video, we ended on point number 4, so we'll start off on point number 5 here, which is potential energy. So potential energy is a special kind of energy, and it has some qualities or characteristics to it. This type of energy is basically stored energy. So a lot of times we describe this energy as stored energy, and it can be used later, converted into kinetic energy, or it can be taken away through work. So we can do work to relieve some of that energy, and that will take it away without converting it to kinetic energy, or we can have a spring that will cause a mass on the end of it to accelerate. And so we will see that stored energy converted into the kinetic energy in the block. So stored energy is a good way of putting it, but it can also be used. So stored energy that can be used to do work. Any potential energy is a stored energy in a sense, but also every potential energy depends on a position. And so you can think of that as being, if I am at some position, ooh, that's really bad. If I am at some position, I can have a potential energy. Think about it like a book on a shelf. If we say 0 is the ground, then this book that's up on top of a shelf, maybe it's ready to fall, maybe it's not, it will have a potential energy because it could fall. Gravity could pull it down and do work, and so that energy would be converted into the work done by gravity. But it depends on the system, like how far above the ground am I? The farther above the ground I am, the more energy I have. Also, the more mass I have, the more energy I have. So that also plays a part. But also a spring force, as you know, is like F is equal to kx. That is going to depend on a distance as well, or sorry, a position. So if I'm at some position in my spring stretch, maybe I stretch out the spring and I stretch out half a meter. And if I'm at the distance of a quarter meter from the unstretched length, then I'll have a different energy than if I was at 2/4 of a meter from the unstretched length. And I'd still have a different energy if I was 1/3 of a meter away. So the position that I am in determines how much energy I am, and that is a hallmark of being a potential energy or a stored energy. And it's usually due to the position in relation to some zero point. The 0 points I'm talking about in those two examples, so for the book, the 0 point would be ground zero. And for the spring, the 0 point would be when we've reached that natural length of the spring. When we reach the natural length of the spring doesn't exert any force. And so it has zero spring potential energy at that point. And we would say that that is our 0 point. And then my stretch distance would be some distance that would tell me what my energy is because I am that far stretched. So this is the potential energy. We're going to skip over kinetic energy and what that is because there's only one type of kinetic energy, but there are multiple types of potential energy. There's one more thing I do want to say about potential energy before we move on, and that is potential energies are due to a conservative force. A conservative force is a force that can easily be done or undone, but one of the big ways to tell if your force is conservative is, does it depend on path? So we say path independence. And we'll talk a lot about path independence, especially when we start getting to friction and stuff. But when it comes to energy, if I think about gravity, and I were to, let's say, have a table. On top of this table is an object, and I walk over and I grab this object. I know that it's some distance, we'll call it y1 above the ground, and so it has some energy because it's that distance y1 above the ground. If I pick that ball up and I move it up to a final distance of y2, y2 above the ground, then it'll have even more energy. It turns out it doesn't matter how I got there, right? If I took that ball and moved it straight up, that's one thing, and I'll have some energy to begin with and some energy to end with. But if I took the ball and I moved it horizontally all the way over here and then started making circles and then even go up and down and all around, whatever, but in the end I end up right here, it doesn't matter that path that I took to get there. What matters is where did I start and where did I end? And so gravity doesn't care about where you ended or where you were in between. All it cares about is where did you start and where did you end. A spring force doesn't care how many times, maybe you've seen a spring, you pull it out, you let it go, and it just goes back and forth a bunch of times. In the absence of friction, it will keep oscillating back and forth forever, but it doesn't matter how many times it oscillates. If it's 1 time, 2 times, 50 times, 100 billion times it's oscillated, if you're at 0.25 meters, you're going to have the same energy every time. And it doesn't matter how many times you did that oscillation, you can always measure the same amount of energy at that point. So when we talk about path independence, it only depends on where you started. So it only depends on starting position and ending position. Path you took to get there is not important. The path between doesn't matter. And that's kind of makes sense for us, right? When we think about what I described. If I move that object up and down, it doesn't matter how many times I move it up and down. It doesn't matter the path that I took to get it from point A to point B. What matters is point A and point B, and anything else in between, not important. So these are how we define what a conservative force is. But in a more practical sense, one thing that you might want to know about conservative forces, let's see, we're on 5E or 5C. 5C. When it comes to conservative forces, and we talk about our path independence, this means that we can look at two positions in this thing's motion and calculate something. And so that a lot of times means that we have an equation for that force. So if you have an equation for a force, it's probably a conservative force. Let's think about that, what that means. I'll make a table. So we'll have conservative forces and we'll have non-conservative forces. Under our conservative forces, we already kind of talked about it, but the spring force, F spring, also force of gravity is conservative. There's this Coulombic force that's conservative. Our strong nuclear, our strong and our weak nuclear forces, those are conservative. Our Coulombic force, I talked about that. That's minus K times charge 1 times charge 2 over distance squared. That's nothing we'll talk about really, but it is still a conservative force. These conservative forces all do not depend on where things were. Well, they do. They don't depend on how they got from point A to point B. They all depend only on where they were and where they're going or where they end up at. But a non-conservative force would be something, like a normal force. We don't know how to calculate a normal force. We have to use Newton's second law or Newton's first law to relate normal force to gravity, or to gravity in some cosine or sine or something. Another thing like a pull force, a push force, a tension force, an applied force, all these forces are not conservative forces because we don't have an equation to describe them. But also because if we don't have an equation to describe them, we have to use Newton's laws. And so Newton's laws is basically kind of this boundary between our system and outside the system. So force of pull, force of push, those things are exerted on a system and they change the energy of that system. Usually they change the velocity, they cause an acceleration. These are non-conservative forces, and they act from outside of the system onto the system to cause it to either increase in acceleration or decrease in acceleration. And so when that happens, they are doing work and they're adding or removing energy from the system. These are non-conservative forces because they add or remove energy from a system. But a spring force, a force of gravity, they don't necessarily always do that. If you define that spring to be a part of your system as well as the mass, then it turns out that the spring doesn't do any work at all. It just converts potential energy to kinetic energy. So that's one big thing. But there is one caveat, and that is friction. So friction, we have an equation to describe our friction, mu k times normal force, or mu s times normal force, something like that. But friction is not conservative. Friction is a special force. Friction is what we call a dissipative force. It dissipates energy. And as you can maybe kind of think, that probably means it is non-conservative. It does not participate in conservation of energy. And that's what we mean when we say conservative. If something is non-conservative and this force is acting in your system, you can't use conservation of energy. You cannot assume that your system has the same energy at two different points because that force will change your total energy of your system. So just an important thing, and the biggest way that you can, or the easiest, clearest way that you can tell whether your force is conservative or not is, does it have an equation to go along with it? So the next thing I want to talk about before we get to some examples the next thing I want to talk about is this idea of a total mechanical energy. So our total mechanical energy, we'll call that E. Actually, no, let's take a step back. Let's not talk about total mechanical energy. Let's talk about this potential energy stuff a little bit more. So potential energy, we have two different types. We'll call this part D. So potential energy, there is a spring potential energy and a gravity. But for spring potential energy, there's a couple things we should talk about. There's a symbol that we use for potential energies, and that is U. But for U sub S, we'll call that our spring energy, and the equation for that is 1/2 kx squared, where x is that stretch distance away from our unstretched length of the spring. It looks a lot like kx times x, or maybe kx times 1/2 x, or something like that. And that's true, and that comes from our work equation, and we'll talk about where that comes from in a little bit more. But for now, just understand that the equation that we use to calculate U sub S, or the spring potential energy, is 1/2 times K, which K is the spring constant, or spring force constant. And X is our stretch distance, or compress. Stretch / compress distance. And again, that's how we calculate it. It's pretty straightforward. If you know X, you know K, you can plug those into your calculator, multiply it by 1/2, and then you'll get your energy out for the spring. What else do we have? Spring energy. It doesn't really matter if the energy, or if your displacement is going to be positive or negative either. If I think about my spring, here's maybe a diagram. We've attached it to a wall, and it could be compressed some distance. Let's say this is our natural length, L naught, or it could be stretched that same distance, right? So in this scenario, call it 1, and this one is 2. So in scenario 1, we've compressed it some distance d. In scenario 2, we've stretched it some distance d. And it turns out that d would be negative d for scenario 1, it would be positive d for scenario 2. If I plug that into my spring potential energy equation, I get d squared, and whether it's negative or positive, that negative gets squared, and so it becomes a positive x squared no matter what you do to it. And so there's no way to make this U sub S thing a negative number. K is always positive, 1/2 is just 1/2, it doesn't ever get negative for some weird reason, and X, well, it's squared, so it gets turned into a positive, and so U sub S is always going to be a positive value. For spring potential energy, you can kind of think about it as just like that energy stored in the spring, and no matter what direction the force is pointing, it'll always be a positive energy. So continuing on to the next part, 5E, we will talk about the other potential energy, which was our gravity potential energy. So gravity potential energy is another thing that's due to position, and it has to do with the Earth and the force of gravity. So when we talk about I kind of hinted this back in the last unit, I said F sub g, that's Newton's universal gravitational law, that's equal to g times mass 1 times mass 2 over r squared, where r is the distance between the two masses. And so if mass 2 is very large, like it's the mass of the Earth, and r2 is the radius, or r squared is the radius of the Earth squared, then what we get is this thing here becomes, n times g, becomes lowercase g. And so we get our force of gravity near Earth is just equal to mass 1 times g. And that's the difference I want to make, or that's how I want to differentiate between gravity potential energy, which is due to this simplified form, Fg is equal to m1g, so that's gravity potential energy, versus gravitational potential energy, which is this one. It's not really much of a difference. It's very subtle, but I still want to be clear about that. When we want to notate something has gravitational potential energy or gravity potential energy, we use U sub g. And to calculate it, we get mgy. So this is the equation that we will use to calculate our gravity potential energy. When we talk, if you want to know what, for all practical purposes, what is useful, this is it right here. U sub g is equal to mgy. This is again due to a position above the Earth's surface, and the Earth's surface is what we'll say is our 0 point. And so then if I'm at some height y above the Earth's surface, I will have a gravitational energy of mgy. Finally, for this part of things, potential energy, I guess, and energies, I want to talk about some symbols. I didn't talk about kinetic energy just yet, and we'll get to that next. But for energy, any potential energy, the symbol is going to be U. And that's my version of a capital letter U. Don't be confused with a capital letter V that I write. They look very similar. I know, I'm sorry. But the symbol is U. If I want to say it's a potential energy due to gravity, it's U sub G. Potential energy due to spring, U sub S. Potential energy due to like a charge separation, maybe I'd call it U sub C or something like that. That's not something we concern ourselves with. It's not mechanical energy. So the mechanical potential energies are just UG and US. Okay, so let's take one more quick look at this kinetic energy thing, and then we'll move on to our total mechanical energy. So kinetic energy is given the symbol T. And the reason for that is because it's French. There's like the French version of kinetic energy, the words for it start with a T. And since the French kind of developed a lot of our system, SI system of measurements, which if you don't know, SI is actually international system, but it's SI instead of IS because it is in French. And it's like Système International or something like that. So that is one of the reasons why we use T for kinetic energy, because at this time, when we came up with the idea of kinetic energy, the French, like these mathematicians who were crazy, crazy smart, guys like Poincaré and stuff like that, they were hugely influential in the development of physics and the math behind physics, and so we use T for kinetic energy. So we say T is equal to 1/2 mass times velocity squared. That is our equation for kinetic energy. This is similar to what I was talking about with UG is mgy. If you want to know what's useful, this right here in the box, that's going to be the most useful thing that you're going to see for the next few minutes. Okay, so if I know something, if I look at this equation, I can think about it as being you have energy because you have mass. And my handwriting is getting so much worse as the night goes on. So energy because of mass and motion, right? If you have velocity, you have to be moving. And so mass and motion give us this kinetic energy. If I don't have mass, I still have kinetic energy. Like photons don't have mass, but they do have kinetic energy. But there's a whole way that we deal with them because they're traveling at the speed of light, and so we have to use like these weird transform things. So not important for us. The important thing is that for kinetic energy, for anything we do in mechanics, is 1/2 mv squared. That is the three equations for energy. I will kind of summarize them here. We have spring potential. That is U sub S is equal to 1/2 kx squared. We have gravity potential, which is U sub lowercase g is mgy, or mgh if some people like that, and mass times gravity times height above the ground. And the last one that we have is our kinetic energy. That is not U, but T is equal to 1/2 mv squared. So those are the three equations that we will be using pretty heavily for the next couple weeks. So pay attention to those, write them down, memorize them, become good friends with them, because if you don't like them now, they're going to come back to haunt you. So Just in the interest of keeping things a little bit shorter, I'm going to stop the recording here. We will pick up with the rest of our energy discussion on the next video, video number 5.